All right, section 5-9 is on the volume of a solid by plane slicing. The objective of this section is to given a solid whose cross-sectional area varies along its length, find its volume. And that's what we've been doing for the first two parts of this section. And now we're going to look at a slightly different technique here. In the previous two parts of this section, we are taking some region and rotating it around some axis, and then finding the volume of that solid of revolution, we call that. It's a solid that's formed by revolving some area around some axis. And now instead of rotating it around some axis, we're going to look at problems where it's just simply a description of some solid, but each cross-section of the solid is going to be a uniform shape. And that's the key for this whole process, that if you're going to use solid by plane slicing, the cross-sections have to be uniform. All right, so let's take a look at an example that illustrates this. It says a 2-inch by 2-inch by 4-inch wooden block is carved into the shape shown in the figure 5.9e. The graph of y equals the square root of 4 minus x. Let me write that down. Is drawn on the back face of the block. Then wood is shaved off on the front and top faces in such a way that the remaining solid has a cross section. Excuse me, the remaining solid has square cross sections. So they're not going to be circular anymore. They're square. That's going to be key for us. Square cross sections perpendicular to the x-axis. It asks us to find the volume of the solid and show your answer is reasonable. All right, so let's draw a sketch of what this thing looks like here, or at least attempt to draw a sketch of what this thing looks like. So let's draw this curve, first of all, that they give us here. They gave us the curve square root of 4 minus x. And again, if you need to punch that in your calculator to see what it looks like, but it's a curve that looks something about like this. And it crosses the x-axis out here at 4. It crosses the y-axis up here at 2. All right. And we start out with this block of wood. And this block of wood would look something about like this if I were to sketch this in 3 dimensions here. I should say the resulting block after I've formed it here by shaving or carving these sides down. You end up with this solid here. Okay. Again, if it helps you draw the solid, certainly do that if you can. You don't have to have that. Really what you have to have is the one slice, but that's kind of what it would look like. You can look in your book there to get a little better sketch of this. Now the key here as far as how I draw in that slice is they got to tell you something about the cross sections and where exactly you have to slice this to get uniform cross sections. Most of the time you'll find they'll tell you that. Sometimes you might have to figure that out on your own. But this one says that the remaining solid has square cross sections perpendicular to the x-axis. So perpendicular to the x-axis tells me I got to draw in my slice here vertically. And if you draw in kind of the rest of this slice in 3 dimensions, it's going to look something kind of like this. All right, and you get this little rectangular solid here. Let's go ahead and name these points here, like we've done many times. I'm going to call this X, Y1 down here, and we'll call this one X, Y2 up here. Right, and just like you've seen on the last several problems that you've done and the last few examples we've covered, once you have this one slice sketched, you then have to come up with a formula that represents the volume of that one slice. That's the same thing we've got to do here. Just the only difference is in the last problems that or the problems that we've been working on, those slices always turned out to be circular. So we were using the formula for the volume of a cylinder, pi times radius squared times the height. Clearly, we don't have a cylinder anymore, so I can't use that formula. I have to figure out the formula for this particular region. Now, this is just a rectangular solid, and actually it's more than that. It's got a square base, they say. The cross sections are square. So in terms of the volume here, dV, it's going to just simply be, since it's a square, I'll call the length of the side here S, but it's a rectangular solid, so I know the volume of it is length times width times height. Since it's square, the length and width are the same, so I'll call that the side squared, S squared, times the height. If you want to write length times width times height, you can. That's fine too. But since I know it's a square base on this thing, it's going to be the same distance on both sides there. All right, so let's replace S and H with what they're equal to. So if we look at our sketch up here, S, you can measure the side length, I guess, a couple of ways. Here's the distance from here to here would be the side length S, which is also the distance from here to here is the side length as well. Now the distance, the second one I drew there coming out of the board there in essence at us is in the third dimension, so I don't really want to work with it. I want to work within the XY plane there, so I want to use that first value that I sketched there. So look at that blue strip there that I've got and measure that distance S. That's just a difference there of those Y values. It's a vertical distance, so it's Y2 minus Y1. And it's that side length squared, so it's going to be Y2 minus Y1 squared times the height. Now the height of this thing, or the thickness of it, this distance right here is the height of this thing, just like we've seen many times. But that corresponds to the same as the thickness of this original slice that we drew over here in the XY plane, and that's a change in X. So that's actually dx. So our height of this is dx. Okay, notice the slight difference in this problem, that I didn't end up with that cylinder like we've seen. So I don't use my formula for the volume of a cylinder here, but I still end up with a volume of some shape that I know. In this case, it's a rectangular solid. I know its volume is length times width times height, or better yet, in this case, length and width are the same, so it's the side squared times the height. And then I go back and I substitute in what y1 and y2 and dx are. So the setup is very similar. The only thing that differs here is my formula that I'm using to calculate dV. In fact, that's the only thing that differs between what we were covering here in this section with volume versus the previous section in area. When you're working with area, you're just simply calculating base times height, because that's the area of a rectangular region. Here, when we're working with volume, I got to find the volume of this one slice and find that formula. Once I do, the work from there looks pretty much the same. All right, look at your differential. The differential is dx, so that tells me I want to get rid of the y values, y2 and y1, and replace them with x values. So y2 is on the curve, so y2 is going to get replaced with that square root of 4 minus x. So it's dv is equal to square root of 4 minus x, and then minus y1. y1 is actually on my x-axis. That's where y is equal to 0. You notice that when one of your points there is on the x or y axis, those end up being zeros, but still put them in there just so you remember them, because in some cases, or many cases I should say, that's not going to be the case. So make sure you include that every single time. All right, let's just simplify this a little bit here. We're going to use our calculator to evaluate it, so technically I wouldn't need to worry about simplifying it, but this simplifies nicely into just 4 minus x, when I take that square root and square it, times dx. And we are all set for integration. So the integral of dv is equal to the integral of 4 minus x dx. The only thing we need is limits of integration. So this is in terms of x, so look for x values here. I want this slice that we sketched in there to go all the way over here on the left. That's at x equals 0. Over all the way to the right, and this is at x equals 4. All right, so limits of integration are 0 and 4. And that's where the sketch definitely helps you coming up with those limits. Sometimes you've seen they give you those numbers, sometimes they don't. Here's an example where they did not, and your sketch will definitely help you out. Again, that one's not too bad. We could use fundamental theorem of calculus on that guy, but I'm going to use our calculator again and use numerical integration. So let me just move this over to the side so I can see that equation. It's just 4 minus x. So FNINT, 4 minus x. My variable is x, and I'm integrating from 0 to 4. And we'll let it crunch that and get a value of 8. So this turns out to be 8. And again, the block of wood was 2 inches by 2 inches by 4 inches, so this is going to be in cubic inches. Okay. Now, in this one here, they said to check that your answer is reasonable again. You could go back to the original block of wood, for example. The original block of wood was 2 by 2 by 4. So the original volume there of the solid would be the product of those, 2 by 2 by 4. So total of 16 cubic inches. So you actually end up shaving off half of the block of wood in that process. And that at least tells me it's reasonable. Okay, I know it's got to be less than that. It can't be more than 16 because I didn't add anything to it. I took stuff away. So there is our answer to that one.